Hi, everyone. My name is Michael Goin. I am a maintainer on the vLLM project. I've been working on it for close to 2 years now. If you've landed something or posted a PR, hopefully I've reviewed it in the past. I'm a principal engineer at Red Hat, previously Neural Magic. I was at a startup since 2019, and we were acquired and joined Red Hat at the beginning of this year, and have been chugging along on open source inference optimization for a long time. So, today for me, you're going to get from the inference engine perspective. I work on quantization, kernels, model features, but also many like application level, and obviously we have a lot of users and customers that require a lot of things from vLLM as an inference engine for efficient RL. And so I want to walk you through basically what are the major things that vLLM has done in order to well support performant reinforcement learning in open source. So first we're going to quickly introduce you to vLLM. I'm going to assume you kind of know how LLM inference works, how token prediction works. So the goal of vLLM is relatively simple to start with, right? We just want to build the fastest and easiest to use open source LLM inference engine. Easier said than done, but we'll sort of walk through what are the key things there. So the first challenge, mind you, this is back in 2023, is batching. The sort of naive padded batching that you did in machine learning, like CV, or really like before transformers, was padded, or before autoregressive models was sort of padded static batching. However, with large language models where we're autoregressively generating and predicting the next token, we don't know how many tokens the model is going to generate, and thus each token is going to be a forward pass. And so if we make a static batch of requests together, like we start all these sequences together, and we're generating tokens from them, and we need to run them until all of the requests have reached the stop token. All this white space for all these time steps are wasted space that we've run other batches of requests that, we're just wasting that space. And so one of the key things there was continuous batching, where as a request finishes, S1 here, we're able to insert in S8 as soon as it's ready, and there's space for it. And through continuous batching, we're able to get much greater utilization out of this fixed batch window that is sort of represented here. Great, that's pretty simple. Next, KV caching. Hopefully you know that as you're generating the output tokens of the model, you can save the intermediate values of K and V, keys and values, in self-attention, and just reuse those, read them from memory for all the previous tokens you've seen, and you only need to calculate fresh values of Q, K, and V, queries, keys, and values, for the next token or the new token you predicted from the last forward pass. This saves a ton of compute because you're able to not keep doing a full forward pass and all the math for the whole model for every token you've seen in the past. You only need to attend to it in attention. However, keeping this KV cache around can actually take up a lot of memory. It wasn't so bad when we had context lengths of 1,000, but as we have models with 10,000 token context length, 100,000, 1 million context length, the sort of roughly 1 megabyte of storage that you need for one token's KV cache obviously varies for model, but a megabyte is a rough estimate. Once you start talking about 1 million token context length, we're talking about tens of gigabytes of data. And once we talk about batching requests together and trying to efficiently serve 100 users at once with one inference server, well, now we're talking about hundreds of gigabytes of space just for the KV cache. And in a lot of modern scenarios where you need really large batching to get good utilization, like for large mixture of expert models like DeepSeek, the KV cache can take up more space than the model weights themselves. So when we're talking about production grade, efficient inference, it's very different from the batch size one, like local inference, where you're just trying to fit the model onto your laptop's GPU. We really need to be cognizant of how much space the KV cache takes and how can we efficiently batch large real-world requests. So vLLM's original innovation was to introduce paged attention. which is where the V in vLLM comes from, sort of borrowing an idea from operating systems of virtual memory by adding in a layer of indirection represented by this block table that from a request perspective, it thinks its tokens and its words are contiguous to that request, one word after the other. But the KV cache for all of those tokens, it can be stored discontiguously in physical memory. So we're able to pre-allocate all of our physical KV cache in GPU memory ahead of time, and then as requests come in, and we need to start using the KV cache, we just start finding whatever block is free, and put the KV cache there, and then just by making the attention operation aware of this non-contiguous nature, you can choose different block sizes for efficiency, we're able to get much greater efficiency out of the physical KV cache space in a way that doesn't require constant defragmentation or general issues you have without having something like virtual memory in operating systems. So here's another representation of that. So you have request A with its logical KV blocks and a block table, and you have request B with its own logical KV blocks and its block table. And in the actual physical KV blocks, these are stored interspersed with each other, and they don't really matter. And a really cool property of this is actually once request A finishes, if request B turns out it needs to go for 20 or 30 more tokens in this really constrained case, it can just start running over the physical KV blocks that request A was using when request A finishes. And we just can greedily free up, or rather, sorry, lazily free up the physical KV blocks as we need to run into them. But if it turns out that request B ends after one more token, and request A is still sitting there in the physical KV blocks, if we have another request comes in that maybe half the tokens are like request A, we can actually just reuse those KV blocks that are already there in memory. This is what we call prefix caching, and this is enabled automatically by a system like vLLM, because we only need to free up the physical KV blocks when we have requests that need to use the KV cache. So if you are serving an LLM and it's getting hit with a lot of similar requests, a lot of the prefixes of the prompts are similar, we're able to just skip a lot of computation, get faster time to first token, and actually even reuse the same memory for KV cache between requests, because they're just pointers in the block table. They're pointing to the same memory. We don't need to duplicate those prefixes. So it's a really elegant idea back in 2023. And so, yeah, it's been a greater than 2-year journey since then from the original research paper that produced page attention and the vLLM project, and it's quickly grown into a huge flywheel of an active project in the open source AI inference community. 60,000 GitHub stars, 100K daily installs on PyPy, over 1,700 unique contributors of landed code, with 100 plus every 2 weeks. And it's a software that's battle tested in production deployments by real companies and users deployed on millions of GPU hours per day. So hopefully you know a bit about vLLM now. I'm not going to spend too much time on optimizations and performance. I'm just going to sort of introduce what the interface is and how you can use it. So it's a pip install away or a Docker pull away. It's an easy to use Python library. And as a result, it offers a Python-based interface for offline batch inference. You import your LLM, you throw your Hugging Face or model scope model in there, and you generate text from it. Pretty simple. Then there's a really key thing that's really useful for people that use closed source APIs and want to host and build services on top of large language models with vLLM, and that's the OpenAI compatible server, which is also a pretty easy to use command, just vLLM serve your model. Obviously, it's pulling from Hugging Face here, but it can be a local directory. It can be in a variety of different formats. And then once it loads and deploys your model on your hardware, it gives you an OpenAI style API with completions, chat completions, tool calling, structured outputs, a variety of other things, which is what we're mostly going to talk about here today for RL. And then finally, there's a low-level LLM engine, which are for the users that want to build their own API servers or their own processes, and they want to have control at the request or step level to provide inputs and deal with the engine core of VLM in an asynchronous, performant way. And this is used for NVIDIA's Triton Inference server, building on top of VLM as an engine core and building their own services and interfaces and orchestration on top of that. So part of the reason why VLM has been so successful is because it offered a really solid software interface for efficiently running large language models. And through defining that software interface, it supports a wide variety of models. Over 200 different architectures are explicitly supported in VLM, many more we don't know about. And it's expanded a lot from just text-only, transformer, decoder-only models like Llama. It's obviously expanded for large-scale mixture of expert models, state space models, linear attention models, cross-attention, all sorts of advanced architectures that we're building on top of and getting released day by day these days. And of course, we've expanded way beyond text-only input, a variety of multimodal inputs, and working on multimodal outputs more and more. And of course, providing raw embeddings to the server as well if you want to do your own preprocessing and bring that outside of the server and control that yourself. Lastly, there's many different tasks. We're not just talking about just the OpenAI API. We're able to expand and provide many more different types of interfaces. Also the embedding API, or offering classifiers, or reward models, useful for RL, or re-ranking for use in vector databases and RAG. So we're able to support many different transformer models because of these basic ideas of how to efficiently run transformers. And through that software interface and the broad adoption of that, the hardware providers have found an opportunity. So while, of course, VLM works to get great NVIDIA GPU performance, many different hardware providers also get great performance on VLM. And they do their own work, just like the model providers do their own work to get their model architectures into VLM, to build and cultivate their own hardware backends, targeting VLM as that software interface for efficient inference, and of course run all those different model architectures. So there's a large variety of hardware accelerators and CPUs, frankly, that have support within the VLM repo, and an increasing number that have out-of-tree plugins and their own open source projects that plug into VLM and implement new hardware backends. There's even more than this, an increasing amount in Asia that we're supporting. So yeah, it's just really cool to see the complexity and different approaches that the different hardware backends are taking that we're able to see through our collaboration in VLM. Next, we only talked about things for running VLM on a single node so far, or a single device, actually. But there's many different types of parallelism and sharding that you want to split up your model in a variety of different ways, depending on your interconnects between your accelerators, so you can efficiently serve models that aren't going to efficiently fit on a single GPU. So I'm not going to explain these. There's obviously a lot of time we could spend on why you want to use the different types of parallelism, tensor parallelism, expert parallelism, pipeline parallelism. There's even more than this that we support. But we're able to mix these types of parallelism depending on the architectures and the hardware specifics that you have. And we're even able to disaggregate the sort of prefill, the prompt processing, and the decoding, the output token generation through disaggregating prefill and decode and transferring the KV cache between different instances of VLM. So yeah, hopefully you understand a bit about what VLM is and why it's important, why it's been adopted for inference. And now we want to talk about how it supports reinforcement learning. These are some of the reinforcement libraries, some of our ones we like or have collaborated with in open source that use VLM as the inference side of the equation for their RL. Hopefully you're going to hear from some of them later today or later in the conference, so they can give a better explanation of reinforcement learning. But I'm going to do my best to keep it very simple and high level from an inference perspective. So you can think of it like most simply as a training loop, again, kind of represented here with a reward model. But basically, we have some prompts, some questions or environments or challenges we want to put the agent through, which the agent is running on your inference server. You predict tokens and do inference with the agent and those prompts to generate completions. And maybe that's in an environment. Maybe that's just letting it run wild and rampant by itself. And once those completions finish, you judge how well those completions were, how well they turned out, how well the agent did on the various problems. And you calculate some rewards for how great it did on those various batch of completions. And then that gives you some information so you can update the weights of the agent and try again with a new batch of prompts, and just keep iteratively updating this model as it, or this agent as it works on your environments or your problems. So I have this lovely diagram shared by Jackman at Prime Intellect, so shout out to him. But this sort of blows it up like a little bit more in really a simple kind of synchronous, like static, kind of classic form of reinforcement learning with LLMs. We'll go into more advanced things from here. But most simply, you have your LLM hosted in two different ways. You have the weights of the model on the trainer, and you have the weights of the model on the inference server, vLLM here. And then we have some sort of orchestrator that's in the middle of this RL loop and getting them to communicate with each other, where the trainer has some updated weights that it wants to give and try out with. It talks to the orchestrator to then update the inference server and update those weights. And then it also schedules like some new requests and completions to run on the inference server and thus the agent. And then based on how those completions go, we go back to the orchestrator and figure out what batch needs to be prepared for the trainer in order to figure out what new set of weight updates do we need to make. And this cycle happens over and over as we're constantly trying to update the weights, run the agent on those updated weights to see how it's been improving, and if it is improving, hopefully, and then check those results again and figure out what the next weight update should be. And here we have like a pipeline where we zoom into this a little bit more and sort of see like these separate processes or hardware that's maybe running. So again, kind of explicitly, as I talked about here, the orchestrator updates the weights, or requests updating the weights. The inference server updates its weights. And then we submit some prompts from our batch or our training set. And we go and send off really the agent stuff is happening here, where the server is running inference, and maybe there's some environment where it's running on. And then we judge how well it did in that environment. And then we kind of retry again if it did terrible. Maybe grab another batch if that's too noisy. And then we go to the trainer. We do a forward-backward pass, figure out how we need to update the weights based on how the model did. And then we request weight update again and continue on and on and on. And hopefully you can kind of see some efficiency problems here if we're like hosting the trainer and the inference server on different GPUs. And you're running it in this like one-step synchronous pattern like this. The trainer is waiting for like an awfully long time, especially if like inference takes a long time. And the inference server is also waiting while the trainer is updating and trying to figure out its weights. So there's a lot of different ways that people, in production and in open source, have figured out, either to share, the memory, either from the trainer and the inference server, or to, break this synchronous dependency a lot, by much better than this. And yeah, we're going to kind of like walk through what some of those useful features are. So the first thing that I would say we kind of focused on was sleep mode. So like it says on the tin, putting vLLM to sleep, basically deallocating all of its memory it has for the model weights, for activations, for the KV cache, storing those maybe on CPU memory or in some way that it can be easily woken up. And this is useful not just for RL, it's useful for serverless deployments. You want to like host multiple models on the same inference server or the same GPU. You want to do A/B testing, try different things. But for RLHF, this is one thing that we call for like co-location, where we only need one set of GPUs now. If we use vLLM to be the inference server on our not a pod or node of GPUs. We do the inference with that, then we put vLLM to sleep. We load up the trainer and do the forward pass on the same GPUs, and then we put the trainer to sleep somehow. We wake up vLLM, and we do the inference. So at least within a static like synchronous pipeline like we went through, we're at least not really needing to need double the amount of GPUs and just have them waiting. We're able to just have them wait while we need to sleep and wake up the different weights in KV cache. And this is really helpful, particularly for like resource-constrained environments. So you'll hear from Daniel from Unsloth, hopefully in previous talks or possibly later today. And they sort of go through exactly what that inefficiency is like if you don't have something like the sleep feature or don't have co-location. So they sort of talk about through traditional RL having like 50% of the space taken by the inference engine, 50% taken by the training engine, same amount of time, same amount of space and model weights, and KV cache in the case of the inference engine, and activations, gradients, optimizer for the training engine. Then if we're Unsloth themselves are able to share the same weights between the training engine and the inference engine, because they're not doing really large scale deployments here. And then even beyond that, when we're able to put the engine to sleep and sort of deallocate its KV cache while the trainer needs to run, we're able to completely share any of the space that's not for the weights between the inference engine and the training engine, and we don't need to keep that space allocated all the time by just putting like the KV cache to sleep in this case when we're running the training engine. Another really key feature is efficient weight updates. So you have your weight updates from the trainer, and you want to update your inference engine. This is like sort of like a key synchronization spot between from the trainer all the way through the orchestrator to the inference engine. This needs to be fast. So like you want to do this like a trivial way. You have like one vLLM process that's your sort of running process, and then you have separate processes for all the different GPUs vLLM is hosting the model on, one process per GPU. If that like main running process is trying to gather all the weights from the worker processes or the training processes, and then updating all of the inference worker processes, that's a really big bottleneck. Why does this main process, driver process need to control everything? Why don't we just make the workers talk to the workers? So this was a really key thing, enabling like flexible weight synchronization, beyond just allowing for efficient weight updates through the collective RPC interface, but making it so that the training worker process can talk directly to the vLLM worker process, and we can do this through different interfaces. But this enables a much faster weight update process. And a great example of this is from the Moonshot team that made the Kimi K2 models, and they scaled up this efficient weight synchronization to a huge scale, updating a 1 trillion parameter model on thousands of GPUs in 20 seconds, which is pretty crazy. We have some sort of like benchmarks here where they show like a Kimi model and a DeepSeek model running on 16 H20s or 256 H20s, and how long it takes to gather and synchronize the processes together and get them to update peer-to-peer or broadcast. They developed this checkpoint engine to manage the training engine and the inference engine, which they used vLLM for the inference engine. So a really cool idea of taking this like feature to the extreme and really pushing really pushing the bottlenecks out of the way when you have these very expensive, large-scale GPU deployments. We're talking about potentially thousands of GPUs that could be waiting for an all-gather, and you would much rather keep them running inference or training batches. Next, we've been talking about this whole time sort of like synchronous RL, where the training runs in one step and the inference runs in one step, and they're sort of waiting or being deallocated while each one is running. This is sort of represented by the conventional RL here from the pipeline RL team. They made this paper and graphic, and they sort of proposed something that's been known to be in the closed model labs for a while, but this is sort of the first mention or one of the first mentions of it in open source. Of doing in-flight weight updates, actually in a pretty aggressive fashion that we found really surprising when they initially proposed this. So actually not even, you see here, you kind of have like the padded batching problem where you submit a bunch of inference requests in one batch, and you need to wait for all those requests to finish if you're going to update the weights. Obviously, you don't want the weights to change during inference, right? But they actually propose that you can just keep the batches running, and then whenever you have the weight updates ready, you can just update the weights in the middle of a request, not even updating the KV cache or clearing anything like that, just acting like the weights have been the same the whole time. And with some key auxiliary things like importance sampling, they're able to get like really good results with this. And like anecdotally, I was talking to a guy with his RL startup last night, and he was saying they recently implemented this on their own stack, and it sped up their process from 3 hours to 40 minutes for their usual like sort of benchmark. So yeah, I mean, don't count stupid ideas out until you try them and see that they might actually work and get huge performance improvements as a result. So this is a great example of open source ingenuity. Next, another key feature that hopefully you've heard about recently, Thinking Machines released, or Horace He at Thinking Machines released this blog on determinism in LM inference. Sort of, you maybe think about the usual thing of, floating point operations on hardware is non-associative. If you do your additions in a different order, you're going to get different results. But there's another problem of sort of batch invariance, where if we're running a request by itself or running a request with 100 other batches or 100 other requests batched together, the actual kernels and attention operations or linear operations or RMS norm operations can do different methods of execution in order to efficiently execute on the GPU or whatever hardware. And this causes non-determinism because we're doing accumulations in different patterns, we're doing different things in different patterns. So we need to sort of re-implement these kernels or restrict them in some way to start to make them to make them deterministic and invariant to the different batch sizes that we have. And we've been working with them and others in the community to implement this in various places in vLLM. And we already have support for working with large MOE models like DeepSeek and on Hopper and Blackwell GPUs. And we're expanding to other hardware platforms and other models as well. And just with like a simple environment variable, vLLM batch invariant, you can start to get exactly the same results, not just at the token level, but at the log prob level, even when you're doing non-deterministic sampling strategies like top K or temperature. Obviously, when you're setting the seed for the non-determinism. But this is really critical for some uses of RL, and particularly for evals, where you want the log probs of a forward pass to be the same on the training worker process as on the inference worker process. And if you're using let's say like JAX to do your training process, and vLLM, which is based on PyTorch, and many other custom kernels to do your inference, those kernels are going to figure out different ways of execution, and they might get different results. So we want to sort of reduce the divergence and hopefully get to one source of truth for the answer between the training and inference process in order to keep RL well aligned between the trainer and the inferencer. Another shout out for DeepSeek R1. Hope you remember the paper introducing GRPO. Recently got accepted and posted in Nature, and in their one of their key diagrams where they overview their RL framework, you can see how they use vLLM exactly in their rollout, inference, and training cycles. So highly recommend reading this paper if you haven't read it when it was on archive. But it's very much sets the standard and a good high-level explanation of all the places involved in large-scale reinforcement learning. Next, I'm going to talk about a bit about how vLLM serves agents in Inference. So assuming you've already trained your agentic models and you want to serve them now and use them in applications, we've implemented the responses API that OpenAI has set as a standard in their interface. Obviously, this was served well by the GPT OSS model that they released that we worked on them with in order to get this well supported. And while there still isn't exactly an open source standard for tool calling and agentic interfaces like the responses API, we would love for there to be one. Hopefully this can be like a decent implementation, and more people can sort of adopt this across different models or start to train them to be usable with the responses API or the Harmony format that OpenAI released. But since then, we have seen great adoption by open source projects, particularly some of the coding agent projects like All Hands and Manus that use the responses API in vLLM to do their best agentic workflows for coding. Next, we also support like the V1 messages API from Anthropic. So I actually just landed this today. We were really excited to land this for a while, and it was just a random contributor from the community. But you can now host vLLM with the messages API. This is just using Qwen 3.4b, and the Hermes tool caller, exactly how you would normally serve Qwen for tool calling. And then you just point, you set your Anthropic host API to localhost 8000, and it's crawling through the GPU model runner on vLLM, and it's calling tools and searching and grepping and doing all sorts of things. It's really cool that we can start to get in some of the proprietary agentic harnesses as well. And I'm personally really interested to start playing around with this more, as I've been using Claude Code quite a lot recently. Shout out to Red Hat for unlimited usage. Another thing I want to highlight, that this was actually from a hackathon recently. So this was done in a day, which is insane. And I love Dota too. So for those of you out there that love Dota, there was Boda, which is a Dota 2 agent that uses vLLM to host GPT OSS 20b. And obviously an agentic harness that they built, I think in Lua, connecting to the Dota 2 game. And then, I couldn't get the video to render well here, but check out the link, and you can see the video that they have. And you can see it puts its actions in the all chat. So you can see what it's deciding and when it wants to move away and when it wants to hit a hero, when it wants to hit a creep. This is really cool. It's definitely not OpenAI or the Dota 5 from agent from before LLMs. But it's really cool that even on a 20 billion parameter LLM running on a 5090 GPU, it can be a usable starting point without any fine tuning, just working within a decent, quickly made agentic harness. I hope we get more usage in video games, modern video games, not Atari, hopefully. So that's all I wanted to cover today. Welcome to the vLLM community if you aren't already a part of it. There's many other projects in the vLLM project other than vLLM itself. In vLLM itself, we're happy to have you. Like I mentioned before, it's a pip install away. If you own some GPUs, highly recommend hosting your models with vLLM on them. Thanks to the huge amount of contributors to the project growing day by day. Like I said, we'd be happy to have you. If you want to join or get involved, recommend looking at the good first issue tag on the repo. Join us in the vLLM Slack, where you can ask dumb questions, and no one will be making fun of you. Everyone was really happy to help. And you can join the various special interest groups if you're interested in multimodality or speculative decoding or post-training and reinforcement learning. We have channels for all of these. Small self-plug, I host vLLM office hours on a bi-weekly basis, where I quickly cover what's new in the latest release of vLLM. Usually there's a lot within 2 weeks. And we host special guests from various orgs like Mistral, Meta, I don't know, I'm having a blank, but all sorts of people from the vLLM community. If you build something cool with vLLM or contribute something to the project, happy to have you as a guest if you want a nice talk. So that's all I have for today. And so if we want to go through some questions, happy to answer.
We have time for one question. Yeah. Who wants to be the one?
I have a question that as the open source model gets better and the inferencing layer gets better, do you see any use cases where, okay, so I can do with open source models, but I cannot do with, say, or not as well on the API calls? Like any kind of examples like that?
You mean like for the closed source, like API?
Yeah, closed source, yeah.
Yeah, absolutely. I mean, I know, do you know like Noose Research? They're like a nice like open source kind of rebellious like AI company. They do a lot of cool stuff. But for instance, they do like they're interested in like some very like unique things with like sampling and like manipulating log probs, or like various other people I know. We have this concept of a logit processor in vLLM that you can plug in anything you want. When you're getting the hidden state or the logits from the end of the model before they're getting fed to the sampler to actually like predict the next token. And there's a lot of things you can plug in there to do like interesting things. One thing that our like research team has done actually is that when you like compress like thinking models too heavily, very often they'll start their thinking section and then they'll just like think forever and not be able to figure out how to stop thinking and actually start answering the question. So we have like a logic processor where like we can set like a reasoning budget in a very like hard way. We can say like we want after 100 tokens or 1,000 tokens, and you're not done thinking, we're going to just insert whatever the end think token is, and then from there the model is like forced to answer. And you can get into a lot of things like from there where and obviously go beyond just like the logic processor or sampler, and you can just sort of hook together very like unique configurations of models. And so I think as people come really build more complex versions of models, particularly like small models fine-tuned on specific things like guarding or like classifying or like rejection sampling or things like that. You can build like really unique systems and things, and people are already doing this. There's like 10,000 forks of vLLM, at least like publicly from the GitHub stat. So plenty of people are like making changes to the inference engine in order to like build some specific application, and you just don't have that capability to like change what the model is doing during serving, especially without training a new model from scratch, unless you can change the inference engine and modify something about that, which is really cool, and what we try to achieve with keeping vLLM easy and hackable while still being really performant as we can with flexibility.